All right, let's start. I hope you are hearing me fine. Let me start with this. All right, so Windows kernel. This talk is going to be about subverting the Windows kernel. So we're going to go through 4 stages on this presentation. First, we have to cover the fundamentals because not a lot of security professionals are in deep on Windows kernel. So we're going to cover those fundamentals. Also, it helps to do a recap so you can understand the second part that is going to be the software development and rootkits. That's the first stage of starting to interact with the Windows kernels, developing for the Windows kernel. And then we're going to cover Windows kernel exploitations. I mean, how can you abuse of the, we'll cover that later, or how can you abuse the Windows kernel to get to do what you wanted to do. And then protections, that's going to be what are the protections that I have to, that I have to fight off, to actually achieve that. And I have a lot of PPTs, but I also have a demo, so I'm going to try to fly through. If you have questions, let's not wait to the end. I'm going to try to cover quickly, otherwise you can keep it, and then at the end, we can do a round of questions and answers. So first, why is this important? You might be aware of. Also, I've seen some of the vendors here as well. They are going into this direction. Basically, the golden era of exploits and exploitation, doing basic buffer overflows and so on, is gone, long gone. So, but the threats are evolving now, and as well the protections are evolving. So we have a bunch of vendors' names, so for you to understand how is this happening. And as you can see, the modern endpoint security is getting a lot of coverage on that, right? So what I mean with this, in a long story short, is like everything is moving into heuristics, into EDRs, into sensors, into telemetry, right? If you want to understand, it's not for this talk, this is not a prerequisite for this presentation, but it's a prerequisite for doing Windows kernel exploitation or developing rootkits. So you need to understand first what is an overflow and their types, how do you do depth bypass, how ASLR works, a little bit of heap management because there is a lot of heap in kernel. Windows internals will help to get the Windows internals books and also the Windows kernel programming book. And if you have some knowledge on assembly, that doesn't help you. You also need to have knowledge on C and C++ because there are a lot of security professionals that skip during the whole career understanding programming, the programming side of it, and they go straight into assembly. But when you look at the compilation of the, in this case, a driver, it will help you to achieve results much faster if you know how to program in C or C++. So the last one is EIP control. If you know how to do a buffer overflow, or if you did your OSCP, everyone says, yes, I take control of the EIP. It's not like that. What you take control is of the flow, right? And that's quite important for Windows kernel exploitation. So first, fundamentals recap. All right. I'm going to cover this quite quick. But basically, you have a division. Well, let's start with the memory. You have a division between the memory that you use in kernel and the memory that you use in user space. Right? You can see here from this, we have assigned 2 GB of system space and then 128 terabytes of system space for 64-bit. There are some sections that are on map, and you cannot access from a user mode application into the kernel space. And this is physical memory. Same applies for virtual memory, of course. This is a virtual memory layout. And and there are some things that you need to understand, and we will talk about it a bit later, on how do you prove the memory. You test if the memory actually is called proof for read, for example, and then you check if the memory can be accessed from kernel from the user. These images were taken from the books. So if you are interested in, go Windows internals. These are taken from there. And on the left side, you will see the structure of how the Windows kernel and the user space works. Basically, it's like a really simple schema, but then you have system process, services process, user process, a subsystem, and then I'm saying subsystem DLLs, and you have different layers of wrappers between the user space and the application after you reach the DLL that is still in user mode, and then after that you go into executive, and in the kernel mode you have the executive, device drivers, and kernel. This talk is going to go through device drivers and how do we interact with user mode, right? All right, and besides that, you have the hardware abstraction layer, and then, of course, you have the hypervisor and some other components as well, but this is to make it a little bit more simple. All right, hope you are not scared yet. Now we're going to cover basic software drivers. So, everyone knows what a driver is, right? Everyone knows? Okay. All right. So a driver is something that you use. It's basically, you can think of like a DLL. It's a library, like the DLL. It's a module that you implement, you put into, if it's a DLL, then you put it into the application, and then you use that DLL to use the functions inside that DLL, and then you can have it statically or dynamically compiled. But in the case of the kernel, you have drivers. So you can think of driver like if there were libraries, so it's easier to put in the box of knowledge in your head. And so you can think of a driver like that, but then when you want to interact with that driver, you cannot just say, okay, I want to use this function of this, that. You have to interact. I'm going to show you later through a dispatcher and how to use IOCATL codes and so on. But this is the basic of a subvert driver. First, you create a device. Driver, create device. Then you create a symbolic link for the device. On the top right, create symbolic link device. Then you define the dispatch routines for each IRP. We'll record what IRP is. And then you have the major functions here. You see the IRP major, create, close, read, and write, and then the device control, right? On the right, then we have something that we will go later, but those are ICTL calls, and then at the end, those are the functions. And then you implement the IOCTL handler, right? All right. IRP and request packages. So I'm just covering the fundamentals, so when we go into the Windows exploitation, it will make more sense. So IRP, request package, is a data structure to communicate between the driver and the operating system. So remember I say you cannot go from user space to kernel, so you use IRP packages to communicate with the driver. From the process, in this case it's IO, that's input-output, request package, and then here I'm declaring the measure functions, and then at the end I'm just calling the drivers through device IO control. Okay, and these are the device input and output control. So those are the codes that are defined and dispatched by device IO control. IO will be selected per IOCTL, per control. Yeah, per control number. It has a number, it has a control code. Here on the right, in this example, so I got the process is communicating with, it's trying to communicate with the driver, it's trying to launch something, it's trying to do an action, and then it's doing it through an IOCTL code. In this case, it's 2222000, and then it's declaring the input data, the length, the output data, and the buffer length. Surely, if you've never seen this makes no sense at all. It's like, this guy is talking rubbish. But I'm gonna show you the code, and then it will make more sense, yeah? Because now it's only theory. Okay, at the end, you get into the driver, and then you get the communication back. You get your response to the IOCTL communication. And that's why I'm going to do just a really quick demo. So you see a driver. So what I'm going to show you here is a driver that I developed, just for this presentation. And then I also have, so I have the driver and the user mode application. And the user mode application is going to run on the user space, and the driver is going to be running on the kernel level, right? And then I'm going to use all these structured IOCTLs and stuff to communicate with that driver. Then I'm going to show you an exploit, and then I'm going to show you more, I'm going to go deeper into it. But first, and all drivers, they follow the same structure. So when you are looking for memory corruption issues or memory or vulnerabilities on other programs, it might be quite difficult to find because then you have to understand the flow of the program, how it works. With drivers, it's a little bit more simple from a starting point because they all follow the same structure. Yeah, at least they should follow the same structure. In the majority, they don't have to, but they must, right? One example is the use of IOCTLs. There are other alternatives to using IOCTLs, like shared memory if you are into drivers. But IOCTL is something that you use typically to communicate with the driver. There are other ways, but typically you will find the same structure. What it means is that if you grab any driver, so if you go system32 drivers and you grab any of those drivers in your machine, and you put it into IDA or Jydra, and you decompile the code, you will see something similar. The structure will be similar to the one I have here, of this driver that I just made. So the structure is going to be like this. So first, your libraries, libraries that you will use in kernel. So it's not that you can just call any library. There are libraries that are going to be implemented for a kernel driver. And then I'm calling external functions in this particular case, but it's not something that is going to come by standard. I'm calling copy virtual memory to interact with the memory, and then IO create driver directly from the kernel. But this is where it goes standard. First, I define the IOCTL codes, and then the structure. Sorry if I go too fast, it's because we don't have that much time. This is basically the IOCTL codes. I have 5 different IOCTL codes. I have attach, read memory, write memory, check writable memory, and kill process. Why? What do you think I have that? So what it's going to do? First, attach is going to allow me to attach a process and then move the process memory from that target process into my target process, into the process. Remember, yes? Can you make it bigger? Yes. There you go. So that's attach. Then read memory is going to allow me to read the memory of a target process. Write memory is almost the same implementation, but the other way around. I'm going to be able to write memory from the kernel. Check writable is basically going to try to write something in the memory of that process, of that user memory process, and if it doesn't succeed, the status is not the good status, so basically 0, then it means that you cannot write it into it, so that's why you have to do check writable. Then kill process and choose killing a process, from target, from my PID. So finding the process PID and then choose calling from the kernel is a different function. It's set W terminate process. It's different. So why is different? Why is important? Because the kernel is higher. It's high on the hierarchy of processes. So you can kill anything from the kernel. Same from read and write memory. You might hear about PPL process, protected process like the antiviruses. They run with PPL. They run with system writes. Same for EDRs. You cannot interact with them. You cannot read the memory of them, and you cannot access the handles. For example, to the anti-malware from Microsoft, right? So MS MPGN. You cannot read the handle of it. If you are kernel, you can, right? All right, then structure. This is the structure that we're going to use to communicate. So basically, we send a package, and then that package needs to have a structure. You define the structure that the package is going to have, right? And then this is the structure for that IOCTL. And then the major functions, create I/O, close I/O, and then the dispatcher, device I/O control. So device I/O control is the one you see here, switch control code, and between the control code is going to choose between the control codes, here 775, 776, and so if that switch is like a nested if, it's going to go to read memory. If the user mode asks for 779, then it's going to go to terminate process. 778 is going to go to bright memory, right? And then it's going to run this function. So the structure is create driver, I/O device control, and then the dispatcher, and then that's the custom code, yeah? Because otherwise, it's mostly a structure, yeah? Right. Then, of course, you have one of the major functions. It has to be, but it's not always like that, driver unload. So you can unload the driver from memory, because otherwise it will keep there. Something interesting to say about, I'm going really fast, but still slow. So when you talk memory, when you talk memory from the kernel, you have to make everything right. So if you load a variable into the kernel, you have to unload it, so free it. So you cannot just leave it there, because it will nothing in the kernel, there is no garbage collector, there is nothing like that. So if you make an error, it will remain there until you reboot the machine, right? So I mention it because of the driver unload. Some drivers, they don't have driver unload, and then what's going to happen? The driver just remain there until, yeah, there is no way to unload it unless you use another driver. All right, and let's see this is the user mode. So what I show you is the kernel application, right? So it's the driver. So it's basically a DLL that is on the kernel, and then a user mode application will ask stuff to do through the dispatcher. And it's going to say, hey, can you do this for me? And this is your response. Can you do that for me? And then it's going to do something else, right? So, who does that? The user mode application. What is the engine or the module is the kernel driver. And we are talking about software drivers. All right, so next you have on the user mode, the same, I have declared here the same IOCTL codes, and then of course the device name, because I need to know what is the device that I'm going to connect to. In this case, it's called kernel pack. It would be whatever. You will find out that name of the device driver that you are reversing to a decompiler. Or you can see it on if you list the Windows object list on globals, then you can find it out. Open driver, then here I'm using all the functions, attach process, terminate process from the kernel, check writable, read memory, so basically using all the functions from the driver. Yeah? This is the main, and the main on that driver, it doesn't look like that. The main on a driver is driver entry. The main on a user mode application is main. So that's a big difference. So if you want to go into the main, if you are disassembling a driver, you have to look for driver entry. And if you want to look for the IOCTL code, you need to find the dispatcher. So then you can see the functions. So basically here I'm just creating the driver and then calling each function from it. Here I have a simple exploit. And here I'm just using one specific IOCTL. IOCTL for kill process that is 779, and then just creating the file to create the device. And then after that, I connect to the device, call device IO control, and then I can ask for a PID, interact with it, and then kill that PID. Okay, enough of demo. Back to it. Exploit classes. So now that you have a little bit more understanding on how drivers works, and remember, whatever you can do on kernel, that's why it's rootkit development, because you can make a software driver and then have that power from the kernel and ask a user mode application to do whatever you wanted from it, right? And you will see some examples from it, but think on what you can do from the kernel if you have kernel power. Yeah? So that's why a rootkit on the on the kernel is basically game over. You have full power of the computer. There is nothing else besides that. There are some protections. I'm going to name a few, but still. And how do you get there? Prior to signing drivers, you could just load your driver. I just give you my driver, and then he load my driver, and then I can connect to it, and then I have my driver in your computer. But now you cannot load drivers just as easy as before, and now you have to sign your drivers and so on. So there are some protections that you cannot choose. You can just go ahead with that. But there are some exploits that you can use to get access into that memory. So different exploit, and now I'm talking about exploit classes. Use after free, dangling pointers, pull memory. Basically, if you know about heap overflows and use after free pointers, then it's quite similar. The way that you implement that is a bit different because you do it from the kernel, but it's quite similar. Race condition, talk-to, and then what else? Boundary issues, and these boundary issues, they are mostly into how do you protect. When I say boundary issues, is how do you protect your driver from user mode, right? If you have something mapped in the kernel and you don't check whatever is coming from the user mode using, as I mentioned before, proof read, and it's the same structure and same implementation for Linux as well. So it's not only the Windows kernel driver. Every other kernel does that. So you have to check if what is coming from the user mode is user mode or is kernel, right? So if you don't check that, then it's basically free for all. Uninitializes or info leak bugs, it could come as well from a use after free, and then you get an info leak. In kernel, at least in Windows, this could be used, for example, to get the base address of other drivers or the driver of the NTOS kernel itself. There are some functions at this moment that you can use for that. That's coming from Microsoft, but it will change in the future. But at this point, you don't actually need info leaks, but you might need in the future. Access control logic issues is basically breaking the logic and giving too much power to the user mode. And then write access and read access, it could be virtual or physical, and the most typical ways are using else stars and direct primitives to access write and read. This is an example of an arbitrary write. This part is going to be inside IOCTL code. This is from a driver, and you see that the mem copy is copying the system buffer, so basically what is coming from the IOCTL, from the user control, and then it's set it there, and then you have control of the file path and the length. So that's a lot. And whatever I'm going to show you here, there is some part, it's fine. Okay, but what can you do with that? I don't know. So what can you do with this? So typical POC. So when you say an overflow or heap overflow, what you typically see on user mode is a calc, right? So you see the calculator popping up. Oh, it's fine. So the POC on kernel is typically this. Is getting the eProcess structure and then getting the token from, in most of the cases, the process ID 4, because that's hard-coded, and then you steal that token, and then you put that token into your new process. So that's how you get the system command, right? But what else can you do? And what I'm showing you here is just a few examples, right? But there are some logic bugs, and this is one good example. And this is from the code that I showed you before, and this is found with a tool called IOCTL Lance. And you can also find it with a driver body that is a plugin for IRA. And this is just arbitrary process termination. You see sit W terminate process. That's the control code, system buffer, and all of this has been found directly from a static analysis using this tool. You can also find it with driver body. I think I have a screenshot of that. And who is using it? Malware is already using it. This is like 6 months, 8 months ago, and it's going for long. It's not just now. This is from killfloor.exe. This is not my screenshot. I stole it from the researchers. This is from the Avast anti-rootkit driver. And you see that is the driver, and then what this malware does, so basically it's a malware that you get infected, and then this, remember I should say that you can only load trusted signed drivers, right? Well, the Avast is trusted and is signed and is installed in a lot of computers, so that's why they bring their own driver. It's called a bring your own driver. That's a technique. So basically the malware will load that driver, yeah? And then after loading that driver, it's going to use that driver to look for, well, it's going to create a tool snapshot, basically create a snapshot of all the running processes, and then from the running processes, it's going to try to use, it's going to use that malware, that malware. Well, it's a little bit of a malware, the Avast, but it's going to use the anti-rootkit from Avast, the driver, to run terminate process from the kernel using the Avast driver, right? Right, so it's the list. Here's choose a snippet of the list, but the list covers all the antiviruses. So it's going to load that, and it's going to do that. And here's a quick screenshot from the code of the Avast driver itself. If the process name matches, the malware creates a handle to reference this solid Avast driver. As you can see, that's the name. Create file, then creates a handle with it. And then once the handle of the Avast driver is created, the malware calls the dispatcher that I mentioned, device IO control, and then it's going to call that IOCTL with the process ID that I already got. So first it goes to a list of antiviruses or EDR names, so CrowdStrike, AVG, McAfee, all of them. And then if there is a match, it's going to get the PID, and it's going to kill it using the driver from Avast. Okay? All right, and this Avast driver is able to terminate the process at the kernel level, effortlessly bypassing the tamper protection mechanisms of most antivirus and EDR solutions. All right. Enough of that. Let's talk about protections in kernel. First, the most scary one that still you can bypass is the VBS, Virtual Asset-Based Security. It's coming from the hypervisor. It's hypervisor protected code integrity, known as memory integrity. What it basically does, if you are talking about vanilla Stack Overflows, you always want to push a shellcode into the stack. You want to mark the stack as an executable, and then you want to run it from it, right? So you want to have write and execution, exec permissions, right? In the most simple way, what the hypervisor does is that you can either have a memory section writable or executable, right? So you cannot have both. And also use their own sys calls as well to get into the hypervisor pages and so on. So isolate and enforce code integrity policy for kernel, enabled by default on many Windows 11. Then you have enforced stack protection that is control flow, and all of these protections, they go mixed together. So you have control flow that is basically checking the flow is similar as what you have on user mode, and then you have shadow stack in kernel mode. I think there is something similar as well in user mode, but basically shadow stack is having a shadow stack of the stack that you are using, and then comparing the flow, the returns of the flow, and if it doesn't match, then blue screen of that. And harden return address against ROP in kernel. They always allocate and manage a shadow stack for each thread and basically compares the rate. That's what I said. Then driver signing, I already explained it a little bit of what driver signing is. Then you have PatchGuard or KPP, kernel patching protection, that basically at random intervals, it will look into specific places, specific critical functions of the kernel, and then if it finds that something has been modified, blue screen of death. And you don't know when it's gonna run. So a way to bypass this is to modify it, do your thing, and then modify it back. Then you also have kernel ASLR, so address space layout randomization in kernel. You also have supervisor mode execution prevention. It's a security feature that has prevented detection and execution of user space, as is similar to DEP. So prevents execution and can be bypassed using ROP. Same for hypervisor protected core integrity. And then SMAP, that's basically access prevention that prevents read-write. So we have SMAP and SMAP, so it's execution and access. Yeah, and SMAP is quite funny because the register with flags AC can be disabled directly from user mode on the application. And then you also have kernel cookies that can be bypassed if you find an info leak or if you get the memory, then you can just get that and then override it with a real one. Okay, and how do you do it dynamically? So how do we approach this? Typically, you will think, okay, I have to approach this from a C++ code. No, there are some tools that you can use to quickly find issues and replay those issues. There are not many. Just don't get your high hopes. But there are a few tools that you can use. I just mentioned a few. IOCTL Lance is one. That's awesome tool to get a quick check on drivers to see if there is going to find something. Then you have the driver body, the plugin for IDA Pro, but it's not well maintained and it's quite old and it's not going to find the stuff like we will not find the IOCTL codes. It's going to miss a lot of stuff because it's old. And then once you find that you want to reproduce let's say I found an issue on a driver, then you can use tools like IOCTL Plus. There are other tools that you can use as fuzzers to get to do that. And how it works, on top you see device path. You need the device name, then the IOCTL code. You need that. Then you need also the input size and the output size for the data that you're going to send to that IOCTL code to the dispatcher of your target driver. And then you can just send it on the left side. And then also you have some history that you can do. Right? So if you say, I found this heap overflow of this way to interact with this driver, you can use a tool like this to reproduce it. But there are some requirements. So what do we need? Exactly as I said. If you are the fuzzer, then you need the IOCTL codes. And then from there, you can send that to the driver through the IOCTL codes. So I made a tool. I'm going to give you that tool. And that tool is going to go over IOCTL Plus. And I improved that tool by using a driver hooker. What I mentioned is you have the driver, right? And then you have the dispatcher, and then you can find the IOCTL codes by reversing the driver. So what I did is I placed a hook, another driver in the kernel that is going to hook the dispatcher, the dispatcher of that driver, and then it's going to, of that specific driver, not of every driver, of the driver that you want, is going to hook that, and every time IOCTL is called, it doesn't matter which one, it's going to create a new TXT file and going to drop the name of the IOCTL, and also it's going to drop the data of it. I'm not going to cover the code because otherwise I have no time, but this is the tool. So it has been expanded. It's based on IOCTL Plus, and you see it can be used to make device I/O control requests with arbitrary inputs. The original tool has been improved with a driver hooker, allowing the user to capture the data. And you can see now you can load the config from the hook that you got, load data from the hook as well. And on top, first you have to start the kernel hook on top right. Then you can select the target driver, the service name, and basically call that driver. And besides the hooker, you can also create a new instance of that driver. Then once it's running and you get a hook, then you get a trigger, the hook is triggered, then you can go into that file and load it, and then you can reproduce it. And this is going to help you. Of course, you also need to have your debuggy and your debuggy machine with WinDBG, RedSync, with Jira, and so on, so you can see what is happening. You can get it from here, and includes everything. So it's the in binary form, also the source code, so you can compile it, modify it, and do like I did with IOCTL plus. I made the IOCTL++, so you can make the IOCTL Rust or something like that. That's even better. So, bonus. First, let me show you the IOCTL+. I think I can go. Let me show you how it works. I have it running here. So this is a tool. And I'm going to start the kernel driver. First, I'm going to remove this that I tested. All right. Okay, this is the driver. So the hook now is on the kernel. So the driver with the hook is on the kernel. And now I'm going to create a new instance of the, remember I showed you the driver that I made for this presentation, that it has also terminate process, choose the same code. I reverse engineered the driver from a bus, and I took the termination, the part that is using for that, and I put it on this one. So we use the same code, but not that one. So use something similar. But it's the same. So basically, well, I need a name. All right, now I have the hook and the driver loaded in the kernel. And now for the device list, I need to select that here. And I'm going to set the hooker on to that, because now I have both drivers, but they are not communicated with each other. Now I'm going to instruct using an IOCTL to the kernel hook driver to start hooking this device kernel pack. All right, now the hooking is ready, but now I need to trigger a hook for that. So I'm going to do that. That's why I also made here in the rootkit folder. How is it here? I should have a release somewhere. Oh, snap. Maybe I don't have it? Nah, it cannot be. Yes, it was there. All right, I don't know why I have 3 copies of the same, but fine. I don't use this laptop, so I just made a VM for this presentation, so I can use it here. But what I'm going to do now is from the user mode, I'm going to call. So basically here, if you are replicating the Avast case, then it's going to be the user mode application. In this case, I have my own user mode application to communicate with the driver, but basically, I'm going to call as IOCTL code from it. I'm going to do it, can do it using the user mode app, like this, that when I connect to it, it's asking me for a PID. It can also do read memory, write memory, and so on from the driver, but let's kill a process. Let's open Notepad. Well, okay, Notepad++. And then let's kill it. So the PID is 10772. 10772. Done. And this is the user mode application. Choose interacting with the driver. But because the hook was in place, now I can go load config from the hook. I can go into where the hooks are, driver hooks, driver, kernel driver, and I have this here. And I can load it. And as soon as I load it, it got me the IOCTL code, the decoded IOCTL code, so I can also see the file access, the method that is using, if they has a device type, and then the function. In this case, it's 775. I think I should have another one. (779). All right, and then I can also load the data. There you go. And you see that this is the data that has been sent from the user mode application. Remember, the hook was in place, what this was interacting with. And you can use the same if you want to look how an IOCTL works when you use your actual antivirus, or if you use tools like Process Explorer or something like that you can see, hey, can I do something with it? All right, so 42A was, so that's why I have here the X2 decimal. So that was the one, that's the PID, right? Because that's the one it captured. And you see that I put it in reverse because it's from memory, so it goes in reverse. So now we are driver, and we can replay that. So, but instead of just killing our own notepad, let's kill something that we shouldn't be killing. Like, I don't know, 4316, that is a system, it's running a system, the handle, and then it's also with PPL. So, 4316. So, DC 10 should be this one, and then we're going to replay it, and it's gone. And so we replayed the hook, yeah, from the user mode application. If this was just like with the bus driver, you could do it as well. And there are a bunch of applications that they do that, and it's not only to call terminate process, right? You can just use it to find your heap overflow or whatever you wanted. All right, next, let's say, wait, there's more. That's from Application System Explorer. And in this driver, using IOCTL code as well, found read-write controllable address. So basically, I can read or write on this driver in a controllable way. And there's also destination controllable, but you see that it goes into the same IOCTL code. That one. And this is from the driver body. And the driver body, this is from IDA. And I run it against basically the same test, and it found that it's using memmove in that function, subfunction 11044. Yeah? And so what you need, as I said in the beginning, you need a device driver. If you want to write the exploit, you need the device driver name that is going to be device list file driver. I got this from the driver entry. You can see it on top. And then here on the right, you see the dispatcher functions. And as you can see, if we go to the memmove, it's in sub 11044, and you see that the 4 major functions, including driver unload, they point to the same. No, sorry, driver unload points to the driver unload, and then the 3 major functions, they point to the same function, the vulnerable function. All right, and this is a reversing of that function specifically, and you can see that inside sub 111A0, you have the IOCTL code that is going to select that one. It's going to check if it matches. If it matches, then it's going to just go there. It's going to go to 11044. All right, and we found the memmum. That's the vulnerable function that basically you can control the buffer, the length, just like the exploit that I showed you in the beginning from a different driver. This is from System Explorer, and it's basically the same exploit. You have control of the buffer, the length of the buffer, and if you manage to see on top, the memmove is also not controlling the length of what you are sending into. Okay, so basically, if you want to take in control of the length of what you are sending to the buffer, then you have an overflow as well. So you have an overflow, and you can take control of what you are sending into. So it's basically game over. So what do we have here? Two issues. First, no proof for read. So whatever we are sending from user mode, it gets executed. So that's completely wrong. That's the fix. So the fix that's the fix. So you should use proof for read, and then get the user buffer, and then the user length, and check where it's coming from by using proof for read. They are not doing that. And then the heap overflow here, this is not what the code should be because the code is bigger to fix it, but neither copy secure the length, that's the length of basically the input and the output. What do we need? The way to local privilege escalation, the IOCTL codes, we have it. 22E0008 and the device name. We got that from the disassembly, yeah, and the hooking. The input buffer, we also got it from the hooking. The 8 is the input, and the output buffer is 1044. That there is no control if we send more. The vulnerable function, we need one, of course, if you want to make an exploit, and in this case, we're going to use memmove, right? The Windows API to get the token address, just to make the POC that I mentioned before, and as just a note, the driver-based address is disclosed by System Module Information class, so basically you can get the base address of it. So goal to get the token is first anti-query system information to quote-unquote do the kernel ASLR info leak to disclose the token address of the process system 4. So basically, you have the system 4, and then you get the token because it's running a system, and then we want the address of it. We're going to map the kernel page with the token to user mode using the mem, yeah? And then override the privileges with a field to change to SE debug privileges, and choose a parenthesis. This needs to be run as admin first, because you are accessing a driver. There are ways to do that without it, but in this case, it's doing it like that. And then spawn a system shell with token of system 4. So basically, we will create a new process. We're going to change this. We're going to look into the process list entry, and we're going to get the token from system 4, and then we're going to put it into a new process. And that's how you get system on local privilege escalation using this driver. All right. That was a lot, guys. I hope it helps someone. If you want the tool itself, you can get it from IOCTL++ from GitHub. Here, there is also the QR code from it. And if you want to start doing Windows kernel exploitation, reading is not the answer. Doing is the answer. So set your Windows debugger, get GDRA, get to play and get to replay the POCs from the internet, and start doing. And as I said in the beginning, it's not the starting point should always be developing. So basically, start programming your own drivers, understand how the structure works, and then after that, you can move into exploitation. All right, thank you.
Thank you. Any questions? Sorry.
Hi. Is there actually something a driver can do to defend being called from user space or specific user space programs?
Sorry, come again?
Is there anything a driver can do to prevent being called from user space? So if I write a driver for an application and I only want this specific application, for example, to call me, I mean, I could sign the request or something, but then obviously I can extract the key, private key from the application, for example.
Yes. So I mentioned well, more than a few protections from the kernel itself, from the operating system, from the kernel. But if you are developing a driver, there are ways to check for the IOCTLs when you receive something. So the first check, if by the structure of the IOCTL itself, if the IOCTL doesn't match the structure, then it's going to get discarded. But then you can also, a simple check will be to say, hey, the target PID is from the process that I'm expecting to receive. If it's not, then choose discarded. But in my experience, you don't see a lot of that implemented. But there is, you can.
Hello. Hi. Not my area, not my expertise, but my understanding is that drivers have bad code. This can be abused, right? So you saw the memory copy or memory problems in the drivers. And I was wondering, what is Microsoft doing in this case, right? So they have driver signing. Is there any programs at Microsoft that look at the driver code and says, hey, your code is not good and this leads to exploitability before the driver is signed?
Yes, they are doing, first all the drivers now, they need to be signed, right? So first you need to send it to Microsoft, and then they are doing a quick check, and if the driver is fine, then it goes, is signed, and then you can use it with your device or with your choose software, right? But just if you go to MediaMark or Saturn, you will see that there's a lot of hardware, right? So and most of this hardware, they use drivers. They share drivers as well, but the mechanism of checking and signing is not as hardened as you think. But if you go and use a Windows server, then it's a different check, right? So they go way deeper into the check. So it's not that they're just gonna give you a signed driver for a Windows server. Besides all the protections that I mentioned, and if you want to look what is going to come next on 2026, then you can, or you can just go and check the insider's preview from Windows and see what is going to come. Be prepared. All right. Guys, if you have any further, there is no more questions? Okay. If you have any other questions, then you can contact me here in the future.
Okay, thank you very much.